In this lesson, we would understand what is curve sketching and how can we sketch curves of derivatives from the given function, as well as sketch curves of the function from the given derivative. The learning goals of this lesson are to determine the relationship between the graph of a function and its derivative, as well as to sketch graph of the function from the derivative and vice versa. After going through the lesson, the students will be able to determine that the interval of increase of the function graph represents the positive derivative. The students will be able to determine that the interval of decrease of the function graph represents the negative derivative. Students will also be able to determine that the max, min, and point of intersection points of the given graph represents the zero derivative, as well as students will be able to determine that the derivative is zero at the critical number. Students will be able to sketch the graph of derivative from the original function and sketch the graph of the original function from the derivative function. Let's understand all this with examples, but before doing so, let's first understand how does a given function graph help us determine how the derivative will look like. Let's say we're given this graph, and this is a function graph that we are given, and we want to determine how the derivative on this graph would look like. As we now know that derivative of a function is nothing but the slope of the given function. Let's say if we are asked to find the slope or IROC at this point, then we would draw a tangent at this point that looks like this. We notice that the slope of this tangent is negative. Let's say we want to find the slope or IROC at this point. Then we notice this is also negative slope. If we are making at this point, this slope is also negative for the tangent. If we make the tangent right at the vertex, we notice it is going to give us a horizontal tangent. And as we know, horizontal tangent means zero slope. Let's say we go further than this vertex and we make a tangent here. Then this would give us a positive slope. Further up, tangent is positive because it's directed upwards. Further up, tangent is again positive. So what we notice here is if we make a tangent line before the vertex, in this particular case, then the slope is negative. At exactly vertex, the slope is zero. On the right side of the vertex, in this particular case, we get a positive slope. We then put all this information in a table where we can now put in the intervals. So the first interval is negative infinity to 4. Then exactly at 4, what happens? After that, we have 4 to positive infinity. And we would then write down the conclusion. As per the original function, from negative infinity to 4, the graph is going downwards. It's the white graph that we're talking about. So we notice this is the decreasing interval of the function. Exactly at 4, we see the min of this function. And way past 4, we see that the function starts increasing because it starts going up. Using this, we can draw a conclusion for the derivative function. And we just notice that the derivative function is negative when the original function is decreasing. The derivative becomes a horizontal line or a zero slope derivative at when the function shows us a min point. The derivative becomes positive when the function is increasing. So we just notice here what happened is decreasing function means negative derivative, increasing function means positive derivative, and a minima point on the function means zero derivative. Let's take up an example where we have a parabola opening downwards. In this case, the parabola we have is opening downwards, so this is the original function that we have. If we are finding the derivative on this part of the parabola, then basically we're looking for the IROC of the tangent line that is drawn at any point before the vertex, so that looks like this. We notice the slope of this line is positive when we change the point, but it's still before the vertex.
we again see a positive slope. Exactly at the vertex, we see a zero slope. Past the vertex is negative slope. Further down, negative slope. We can again fill up this table. Here we have the interval from negative infinity to 2. Then at 2, we're going to write down what happens. Then after 2, that is 2 to positive infinity. Looking at the original function first, from negative infinity to 2, the original function is increasing. Exactly at 2, we see a max point. Then from 2 to positive infinity, we see the function is decreasing. Let's draw the conclusion for its derivative, because derivative represents these blue tangent slopes. It's positive from negative infinity to 2. At max, we see a zero slope. And after that, we see a negative slope. That means when the original function is increasing, derivative is positive. When the original function shows us a max, derivative is 0. Original function shows us a decreasing function interval, the derivative becomes negative. So we can now definitely conclude that if the original function is increasing, derivative is positive, and at max of the midpoint or the vertex of the function, we see the zero derivative. Let's say if we were asked to make the graph of the given function's derivative, then we would first have to note this very important thing that states the degrees of the function and relates them with their derivatives. So if the original function is degree 2 function, the derivative will always become degree 1 function. Or if the original function is degree 3 function, the derivative will be definitely degree 2 function. Because derivative will always be 1 less than the original degree function. We can see that when we are given a function equation. Let's say we have a function as 3x cubed minus 2x squared plus 5. And if we need to find its derivative, we apply derivative rules. We get 3 times 3, 9x squared minus 2 times 2, 4x. And derivative of 5 is 0. Here we note this clearly, this is a degree 3 function. And this is a degree 2 function. So the derivative will always be 1 degree down the original function. Therefore, if we're supposed to make the derivative graph of this function, let's say, we would just see what we would do is, we know we are making a graph of f prime x, or the first derivative, and it is going to be negative from negative infinity to 4. Negative on the graph means the graph is going to be below the x-axis. So the derivative function will be below x-axis up till 4. At 4, it will show us a 0, means it will cross the x-axis at 4. And past 4, on the right side, it will go above the x-axis. Since we know the original function is degree 2, so this would be degree 1. And degree 1 is a linear graph that shows us a 0 at 4. We can always make the 0 first. Before that, the derivative graph is supposed to be negative, means below the x-axis. And after that, it is going to be above x-axis and a line going through this point. So this line represents the graph of the derivative. If we want to use the information given in the second graph and make a derivative graph out of it as well, so what we would do is, we first always mark the 0 point, which is at 2 in this case. The graph is supposed to be positive, means above x-axis. The derivative graph after 2 is supposed to be negative, means below x-axis. So the line is going to be made this way. And this is also degree 1, that is the linear function, because the original derivative function was a degree 2 function. Let's say now we're given a function that we clearly see is a degree 3 function. As we are well aware of the basic graphs from the prerequisite courses, we know this particular graph is going to be a degree 3 graph. And if you're asked to make the graph of its derivative, that would be f prime x graph. we would first turn the given graph's information into a table. And since the original function is a degree 3 function, the derivative function will be a degree 2 function where we would see a parabola. As we noted in the previous examples that we have just covered, that max and the min points are very crucial towards sketching the graph of the derivative function. So we'll just look here and we notice before this max point, when we draw the tangent, the slope is going to be positive. Exactly at max, it's zero slope. After that, it's all negative, where the function is decreasing. Then we see the zero slope again. When the function is increasing, the slope becomes positive. So we can say max and min points, or the turning points, are the deciding factors towards making the graph of the derivative function. We would complete this table first. The interval we would have here is going to be decided by the two turning points. So here we have negative infinity to negative 1. And exactly at negative 1, then negative 1 to 3. Then what happens at exactly 3? Then 3 to positive infinity. We notice from negative infinity to negative 1, the original function is increasing. At negative 1, we see the max. From negative 1 to 3, we see the increasing function. Exactly at 3, we see a min. Then from 3 to positive infinity, we see an increasing function. This helps us conclude how the derivative function would look like. So where the original function is increasing, derivative is positive. Where the original function shows us a max, the derivative is 0. Original function shows us a decreasing function, derivative becomes negative. When the original function shows us a min, derivative is 0. Original function shows us an increasing function, the derivative is going to become positive. We use all of this information to sketch the graph of our parabola, because the derivative is supposed to be degree 2, means it's going to be a parabola. We always start by making the zeros first. So for the parabola, we're going to see a 0 at negative 1, as well as we're going to see a 0 at 3. Now the turning point for the parabola is always going to be right in between negative 1 and 3, which should coincide with the middle point between the max and the min of the original function, which we would see is at 1. This point is also called the point of inflection, because here, this point that is right in between the max and the min, or right in between the min and the max of a given function, is also called point of inflection. Point of inflection in the later lessons we would learn is the point where the function changes its concavity. And at point of inflection, we would always notice that the second derivative, not the first derivative always, but the second derivative is always going to be 0 at point of inflection. However, these kind of point of inflections where we see a slight flat line, because if we try to draw the tangent line to these points, we would see a horizontal line. Let's refine this as well a little bit. So this is also point of inflection. And when we try to draw a tangent at this point, it will be a 0 slope. But not at this point we would see the first derivative equal to 0, but definitely at all of these 3 point of inflections, we would notice the second derivative to be equal to 0. However, we will go over point of inflections in the later lessons as well in details, where we would be discussing the second derivative and its relationship with the original function and the graphs. Let's now come back to making the sketch of this derivative graph. That's the first derivative that we were making. So since we know the first derivative is positive from negative infinity to negative 1, negative 1 and 3 were our zeros. The turning point of the parabola is supposed to be right in between negative 1 and 3, that is at x equal to 1. Since the function is positive, means it's going to be above x-axis, so it comes from here, keeps going down until we see the turning point in the derivative function at x equal to 1. We notice here that the function is positive from negative infinity to negative 1. At negative 1, we see a 0. From negative 1 to 3, the function will be all negative, means it will stay under the x-axis. So negative 1 to 3, the function stays under the x-axis, and way past 3, it becomes positive again. So just remember, the turning point needs to be at x equal to 1. Since we don't know what is the y value of the turning point, so if the graph is made like this is also the correct graph. It's just that we need to see a turning point at x equal to 1. Doesn't matter what's the y value. And the zeros should be at negative 1 and 3. So both of these green graphs are the correct representation of the derivative function. And this is how we make the derivative graph of degree 3 function. The best way is always to turn the information into table form. As we know, the turning points are the important points that help us decide where we see the zeros, and then the graph can be sketched before, after, and in between the turning point. Now let's take up an example where we're given the derivative function graph and we are supposed to make the graph of the original function. Let's say we're given this graph, and this is the graph that represents for the derivative function, and we are asked to sketch the graph of the original function, that is f(x). We first decide upon the degrees and the look of the graph. Since the derivative function is a degree 2 function because we see a parabola, the original function in this case would be degree 3 function as we're going in the reverse direction. As we know from the previous examples, when we go from the original function to the derivative function, so when we go from f(x) to the derivative function, we check the turning points and decide on the zeros from the turning points. However, if we are looking at the derivative function and making the graph of the original function, we start by looking at zeros and get the turning points from the zeros. So this is what we will be working on in completing the table first. Since for the derivative function we have to look at the zeros, we notice one zero we have is at negative 6 and the other zero we have it as negative 1. So we'll mark our zeros here, negative 6, negative 1. And then before the zero, the first interval we notice is negative infinity to negative 6. The next interval we would have is from negative 6 to negative 1. We're not going to worry about our turning point because turning points we only see when we are looking at the original function, and we have to draw the sketch of the derivative function. For the given derivative function, when we have to make the sketch of the function, the original function, then we just look at the zeros and not the turning points. The next interval that we would have is from negative 1 to positive infinity, and using this we would fill our table for the derivative function and draw the conclusion for our original function. We know the derivative is 0 at negative 6 and negative 1. Before negative 6, that is from negative infinity to negative 6, the derivative is negative because it's under x-axis. In between negative 6 to negative 1, it's all positive, that's above x-axis. Then from negative 1 to positive infinity, it's again under x-axis, which is a negative function. So we can write down here that when we are looking at the derivative function, we're looking at zeros and the positive negative intervals, whereas when we are making the graph of the derivative function from its original function, then we are looking for turning points and increasing decreasing intervals. So coming back to filling up the table, the derivative is negative in this section. So the original function, we just have to conclude looking at this, will be decreasing. The original function, when the derivative is positive, means increasing. When the derivative is negative, original function is decreasing again. When the original function is decreasing and then increasing in the following interval, so it's the preceding interval and the following interval, we will always see the min at that zero. We also can call these zeros as critical numbers, as we know from the previous unit what the critical numbers are, so we can apply that here because we know negative 6 and negative 1 will represent the critical numbers. Then if the preceding interval is increasing and the following interval is decreasing, we would always see a max at that critical number. So this would show us a max. Using all of this information, we can make the sketch of the original function. So when we are making the original function, we would first start by plotting the max and the min points. That's the vertex. So we would see a min at -6. That will be somewhere here. It doesn't matter where you're going to put your point because we don't know what's the y value. That's the reason we call it a sketch. We don't say we're drawing the graphs because we don't know exact points. Then the max will be at -1. We can make it anywhere we feel like. Definitely, the turning point of the derivative function should show us the in-between point or the point of inflection between the min and the max of the original function that we just saw in the previous example. So the function is going to be decreasing up till -6, hits the min at -6, keeps going up and hits the max at exactly -1. Because it's increasing from -6 to -1, shows us a max at -1, and after that it starts decreasing again. Now we notice this point is right in between the min and the max, also called the point of inflection, where the second derivative is supposed to be negative definitely, but we don't worry about that here. We just were supposed to get the sketch of the original function, which we have now sketched using all of this information. So this is how we sketch graphs from the given graphs of derivative or from the given graphs of the original function.